Okay, so yeah, so looking at multiple linear regression today, uh, we're going to be talking about the multiple linear regression model itself, how we can assess how well our model's fitting the data for a given data set. We'll look at how we can construct new predictor variables from current ones. Sometimes this is called like feature engineering, which I think is a really fancy way to say calculating a new variable using variables we already have. And how we can compare two different models that we've fit for the same data, how we can decide, well, which one should we trust more, maybe. And we'll talk about that. And to do so, we're going to be looking at an example data set on the Great Lakes. So this is real life data, which I like to use when possible because it often has extra challenges that are unexpected or patterns that are not as clean or nice as like fake data typically for class. So this data was collected from the organizations called the Great Lakes Observing System. Essentially, it's an organization that has organized data collection efforts from various buoys across the Great Lakes. Okay. So there's this picture shows it a little bit, but there's these different buoys in the Great Lakes, right? These huge, yeah, often yellow things that can collect a lot of measurements about like water temperature, wave heights, wind speeds, all kinds of things. And they just record data all the time, right? And they use this to monitor the Great Lakes, see if anything's, just to keep track of trends across time and improve our understanding of the Great Lakes. Okay. So these buoys are owned by a lot of different organizations, but this organization has consolidated and like got people to volunteer to give their buoys data that it's collecting across all these many locations throughout the Great Lakes. So it's a really cool data set. It's a really cool organization. If you can go to their website. They always have new data. They have that brand new data portal. They renamed it Siegel. But it has a lot of really cool data. Made this really cool map to showcase some of their data. So each of the points like on here is a buoy where they're like collecting data. So they have buoys like all throughout the Great Lakes and even, so even like in Lake Ontario over here in like by Canada. Okay. And the green buoys, I think, are active right now, but then there's some that they recover at the end of the year when it like freezes over so that the buoy doesn't get damaged. So they still haven't put all of them out yet, but eventually they'll have many, many more buoys. And it's kind of cool because you get this whole network where you have lots of data being collected all the time. And so you can, there's a lot of possibilities for what to do with that, right? So we're working with some data that I grabbed from that system in the fall of 2021 on just 2 days in particular, September 22nd and November 9th. And so the variables in this data set, like each buoy has an ID number. We won't really use that for analysis, but the variables we're going to be focusing on are the water temperature in Fahrenheit that the buoys recorded. It recorded the wind speed in knots, which is kind of similar to miles per hour, but slightly different unit of measurement. And then the peak wave height in feet. Okay. So it measured how tall the waves were. And so here's like a subset of the data, just 5 randomly selected rows. So you can see, again, it's data across all the Great Lakes. So there's some from Lake Erie, Lake Michigan, got like the peak wave height, the wind speed, water temp. Okay. So this was very warm. It's almost unbelievably warm for 76 degrees. I don't know if I believe the water was 76 degrees in Lake Michigan in September, but maybe it was really warm then, I guess. But it seems like maybe the buoy was sitting in the sun. But yeah, so we're going to be using multiple linear regression where we can use more than one predictor to model a quantitative response variable. And specifically, we're going to be looking at modeling the peak wave heights. We'll see if we can use other information that we know about the lakes at that time to predict what the peak wave height is. Okay. So just starting with some exploratory data analysis, it's always good to start with some plots to see what the data looks like, see if there's any outliers or maybe miskeys, right? Like I think I noticed for some of the data, there was some nonsensical values right away. Like maybe there was negative wind speeds or like negative temperatures for the water, which is nonsensical, right? Like it was a buoy error in terms of how it was giving the data. So always got to look out for things like that. So you can remove, there can't be a negative wind speed. So that needs to be like removed. But yeah, now that we've got the data here in this nice format, we can already see a little bit of a relationship here in the data between wind speed and wave heights, which maybe is not too surprising, right? And so this is because we have just the 2 variables, wind speed and wave height, that are both quantitative variables. We could model this using simple linear regression, which we've already looked at and talked about, right? And so if we pull up the guide document, okay, we can give the estimated regression equation. Okay. So if we look at the guide document, yeah, we can just copy the blueprint one. And then we will paste that in here. Okay. All right. So here we're predicting, we want to predict or model the wave heights, the peak wave heights, using the wind speeds that the buoys recorded. So in that case, we would say y hat is the estimated or predicted wave height, right? And then it's always important to give the units of measurement. So we'll say it's the wave height or the peak wave height in feet. And then what about x? What is x in this case? Wind speed, yeah. And then wind speed in knots. It's important to specify that it's in knots here, because certainly I think most people would probably assume miles per hour. But a little bit of a strange units of measurement here. And then we'll give the estimated regression coefficients as well. So what should we replace beta not hat with based on the output? Yeah, the estimated intercept. So we'll just, yeah, we'll round out to 3 decimal places here, I guess. So 0.032, which we got from here. And then the slope we get from right here, right? So 0.199. Okay, so for the estimated equation, we give it with the numerical estimates for the betas, like that. So we're just starting off with a quick review of simple linear regression before we step into multiple linear regression, just to highlight some of the differences too, because they're actually very similar, but there's just, yeah, some subtle differences. And so, yeah, we have the blueprint interpretation for the slope in the guide document, but does anyone want to give a crack at how we could interpret the slope here?
For every 0.199 knots increase in wind speed, the wave height increases by 0.032 feet.
Yeah, really? Okay, yeah. So let's see. So for every 0.199 knots increase, yeah, increase in wind speed. Great, yeah. And then important phrasing is to include either saying we expect or I'm sorry, for every, let's see. See, let's think about how we, so yeah, it's for every something knots increase in wind speed, we expect a blank increase or decrease in the peak wave height. And what do we replace in these blanks here? What's in the first blank? For every one, right? Yeah. So for every 1 knot increase in wind speed, we expect a so if you think about x as the wind speed, and as it goes up by 1, y hat will go up by 0.199. Yeah. And then is it increase or decrease? Increase, right? Yeah, because the slope is positive, we say increase. And this phrasing of we expect is very important to include in the slope interpretation. Okay. Statistics is all about communicating very precisely what the data is telling us. And here we're describing the average trend or the expected trend between the variables. Okay. But we can see from the plot that there's a lot of variability. Okay. So maybe we have this straight line relationship that we expect, something like that. And we're saying we expect for every 1 knot, oh, it says miles per hour. For every 1 knot increase in wind speed, we expect wave height to go up by 0.199. Okay. But that's not exactly how every observation follows. They don't all follow that trend perfectly. So that's why we say, like, this is what we would expect, or on average, this is how much the change is. But it's important to distinguish that from making a definitive statement about that relationship. Just communicating our uncertainty a little bit. So. What about the intercept. How could we? Yeah, let's practice interpreting the intercept here, the estimated intercept.
And then we when speed is 0 knots, the wave height is 0.02 feet.
Yeah, so when there is no wind, so wind speed equals 0 knots. And similar to the slope, we'll say we expect, just to communicate that that's like our best guess, but it's not definitive. We expect the peak wave height to be 0.032 feet. Important to include those units of measurement, right? Yeah. There's lots of problems where the intercept doesn't make sense to interpret in context for a number of reasons. Does that seem to make sense here? Yeah, it actually makes sense here. If there's no wind, we can certainly predict what the peak wave height is going to be. Like, it's sensible from a practical perspective like that. What about from a perspective of extrapolation? Thinking back to what that means.
There's some data points with 0.
Yeah, there's some data points at 0, so actually extrapolation is not a problem here either. So this intercept is good to interpret. Like, we can do that. It's always like those sort of like two considerations. Does it make sense in that context for x's to be 0? And then 2, is it extrapolation? Is that, even if it's sensible, is it in the range of the observed data? So here it meets both those. So so this is sensible in this context because a wind speed of 0 is in the range of the observed data set, and a wind speed being 0 in general is a possibility. Okay. All right. I put that on the wrong bullet though. Okay. So that was a review of simple linear regression. Any questions about how we gave the estimated equation or interpreted the coefficient estimates? Okay. Okay, so simple linear regression is a great model, but it only allows us to model the relationship between one predictor variable and one quantitative response variable. Sometimes we have a lot more information at our disposal, right? So in this case, like we had water temperature recorded by the buoy and wind speed and the wave heights. Okay. So if we want to use more than just wind speed to predict wave heights, we can do that using multiple linear regression, where the multiples are referring to multiple predictors. So here, for example, we can look at a plot of the temperature recorded by the buoy and the peak wave heights. How is this looking relative to the wind speed and the wave heights. Yeah, not as much of a relationship going on, which thinking about what we know about how waves work, right? That's probably not surprising. Like the windier it is, the taller the waves are going to be, right? But temperature is maybe not as much. Like it can be windy and cold, or it can be wavy and cold, it can be wavy and warm. Right? Not as clear. But this is where, linear regression as a model helps us out, because we can just say, well, let's let the data figure it out. Let's let the data tell us what's going on here, since it's not super clear from the scatter plot. Okay. So we fit a multiple linear regression model using SAS, still modeling the wave heights in feet, but now using wind speed. It's actually in knots as our predictor, and the surface temperature of the water in Fahrenheit, okay, also as a predictor. Right. So yeah, let's give a statement of our estimated model now. So just like I have the blueprint for simple linear regression, it's in here for multiple linear regression as well. Make this a little bigger. This one we have to be a little more careful with when we give the model statements, because this is even more general, since you can have an arbitrary number of predictors. So we have to make sure we tailor it for the given problem that we're working with. Okay, so yeah, we start off like this. Okay. Y hat is still the estimated or predicted. And what are we going to say instead of response value here? Yeah, wave height in feet, right? Should say Jace.
What about the assumed theoretical one above?
Yeah, we could give the assumed model as well. Oh, did I skip the bullet? Okay. Yeah, jump to the gun here. Okay, so let's finish this one out, and then yeah, thanks. We can go back and do the assumed model. So we defined Y, and then we also want to define each X. Okay. And now for this model, how many X's do we have? 2, right? Wind speed and temperature. So in the model here, what we'll do is actually already give through X2. So we will get rid of that like that. And if we had 3 predictors, we would need to add beta hat 3 times X3 into the equation. And then Xij, so we'll say X1j is the jth observation of, and then instead of saying the ith explanatory variable, we'll say the jth observation of wind speed, knots. Oops. We can copy that. And then X2 is the jth observation of water temperature in Fahrenheit, right? Fahrenheit's always a little hard to spell. And then knowing what we did with simple linear regression always, what probably needs to be updated here too?
Number of observations.
Yeah, that's true. We could say, that's a good point. How many observations do we have? Oh, I guess it hasn't said in the output yet, but if we go down, we have using what we know about the ANOVA table, which we hadn't talked about yet. This bottom cell here in the degrees of freedom needs to be n-1. So we have 69 observations here. So we can say, yeah, that's a good point. Instead of n, we should say 69 observations. And then what else do we want to update for the estimated equation? Yeah, the beta hats, right? We want to give the numerical estimates from the output. So here, and we can just do it to like 3 decimal places again. So the intercept we get from here. So everything's got, yeah, all the beta hats are going to come from the estimate column. Beta hat 1. So the important thing is making sure you match, like, okay, we said x1 is wind speed, so we'll make sure we get the coefficient for wind speed when getting x1. So this is 0.203. And then we actually have minus 0.001. That is the estimated multiple linear regression equation. Any questions about how we wrote all that out? Okay. So I guess before we go back up and write the assumed regression equation, what do we notice about the slope for wind speed in this model compared to the simple linear regression model? We have this. It's a little bit higher, but very similar, right? But it's not exactly the same. Okay. So intuitively, it might seem like, well, we estimated the relationship between wind speed and wave heights. That should be the same, even if we added more predictors to the model. It may seem that way. But in general, it won't be. And actually, I would say it's more often the case that usually they're not super similar. It just happened to be in this case because the temperature and wind speeds were very unrelated. If you looked at like the correlation between those two variables, it's probably quite close to 0. So that's why that happened here. But otherwise, in general, you can get different coefficient estimates quite a bit for the multiple linear regression model than a corresponding simple linear regression models. Okay. And we'll talk about why that is when we interpret the coefficients. But yeah, let's give the assumed model, since this sort of got ahead of ourselves. I did that one first. So we can copy this from the guide document again. And we'll do this. It's a similar process to how we updated it for the estimated equation here. So we can, right, so we'll update n to give the sample size. And the definition of the x's is actually always the same for the assumed and the estimated model. So we can save ourselves a little bit of work by just copying those exactly like that. And then what should we update in the equation itself up here? Yeah, get rid of the extra, because we only have 2 predictors. Okay. So we want to make sure we get rid of that. That's a common mistake, I think, is to accidentally forget to tailor this equation based on the number of predictors. Okay, so we always want to do that. And then there's really only one more thing we should update about this, actually. Yeah, what the response variable is. So yj is the jth observation of the wave height in feet. So we don't have numerical estimates for the betas for the assumed model. Okay. This is just what we're assuming holds true for the data, but we get estimates of these betas based on a data set, and then we denote the estimates with beta hats. Okay. And notice we still have the epsilon term in the assumed or theoretical model as well. But we don't have an epsilon in the estimated regression equation. So yeah, we've given our estimated model, our assumed model. Okay. We could use our estimated model now to get predicted wave heights based on if we knew the wind speed and the temperature out for the day based on the buoy. But let's talk about how we can, before looking at predicted values, let's talk about how we can interpret these slopes and also the intercept. Okay, so before we said we interpreted the slope as saying for every 1 knot increase in wind speed, we expect this much of an increase in the wave height. Okay. The interpretation is very similar now for multiple linear regression. I mean, we have to change the number based on the new estimate. But the phrasing is nearly the same, except there's a key difference. So now, and I give the general interpretations here. Now we have a general blueprint being for every 1 unit increase in xj, we expect y to increase or decrease by this many units on average. Okay, so that part, this is exactly the same as for simple linear regression. through that part of the interpretation. The new part for multiple linear regression that we add on is saying holding all other predictors constant. This is the key part that makes, like this is the underlying reasoning why the numbers are not exactly the same for the slopes. Because this is a description of the relationship, assuming that everything else is constant. All other predictors are constant now. The idea being that if you want to describe like the relationship between wind speed and the wave heights, we need to do that at a fixed temperature. Like say, okay, make it 70 degrees, and now let's talk about how the waves change as the wind changes. But we can't describe as easily what happens if the wind and the temperatures are changing simultaneously, how the waves change. That gets more complicated. We can't describe it in like just one sentence. And maybe that's more clear, like looking at the effect of temperature. Like if you want to describe how temperature affects the waves, it's really important to fix it at a given wind speed. Otherwise, if the wind speeds are varying too, that just gets really messy. Okay. So yeah, starting with wind speed, let's start with our interpretation from simple linear regression. Okay, but we'll change the estimate. And then we also want to, instead of saying very generally, holding all other predictors constant, we want to say what the predictors are. So in this case, we would say holding, and what's our other predictor? Yeah, holding temperature constant. And then our estimated slope was 0.203. But so again, just pointing out some things that are commonly forgotten. This part, super important. Maybe I'll bold it. So given this interpretation, does anybody want to give a try for the effective temperature? Yeah.
For every 1 degree increase in temperature Fahrenheit, expect the wave height to decrease by 0.0 feet, which holding wind speed constant.
Yeah, great. Yeah. Every one, oh wait, I messed that up. For every 1 degree. Why am I struggling with that? Okay. Every 1 degree Fahrenheit increase in temperature. Yeah, there we go. Thanks. We decrease, yeah, by so we always say for every 1 unit increase in the x, that's always the same, but we say decrease here because the slope was negative, right? Estimated slope was negative. So this sort of quantifies or describes how the scatter plot looked to us, right? Like it didn't seem like there was much going on between temperature and the wave heights. This kind of describes it because it's saying as it gets 1 degree warmer, the peak wave height barely changes that we would expect. Whereas, yeah, for the wind speed, it was, much more, much bigger increase. Like 1/5 of a foot is decent. What about the intercept? So let's copy the blueprint. So how could we interpret the intercept here, tailoring it to this context?
Expected value. Wave height.
Yeah, the expected wave height in feet. Right, yeah, we'll just say it at the end. The expected wave height given that. Yeah, so we can say given that there is no wind, so wind speed equals 0 knots, and the temperature is 0 degrees Fahrenheit, is, oops, thanks. And what do we put in place for the beta not hat? Yeah, 0.136. 0.136 feet. So is this appropriate or sensible in this setting?
Oh, no.
Yeah, so what do we, so the wind speed's okay, right? But the temperature, so why is the temperature problematic?
It would be frozen.
It'd be frozen. Yeah, right. Knowing what we know about the lake, you don't really need a predictive model to say like, what's the waves going to look like if it's 0 Fahrenheit? It's just going to be frozen, right? It's going to be flat. So, I mean, if we were talking about like the ocean, maybe I think even salt water freezes most of the time at that temp. But, right. So since 0 degrees Fahrenheit would mean the lakes are frozen, is not sensible in this context. Okay, so that's sort of like, again, there's like 2 factors to consider. Is it sensible, just knowing what we know about that given scenario? And then 2, is it extrapolation? Is that outside the range of the observed data set? Okay, so sensibility is problematic here. What about extrapolation in regards to that? It's also extrapolation, right? Which we can tell by looking at the scatter plot. Okay, 0 degrees Fahrenheit, way outside the scope of the data. So we cannot interpret the intercept because of that. It doesn't make sense to interpret the intercept. Oh, the reason being, essentially, we can only describe the relationship in the range of data that we saw. We can't assume that that goes on for forever either way, right? So it sort of separately is inappropriate to interpret So note that for multiple linear regression, you need all the x's to be within the range of the observed data. Okay. Whereas simple linear regression, we just had one predictor that we needed to worry about. Now it's more difficult. And technically there's even more constraints on that, but we'll just leave it at that. Yeah, like a purist statistician would actually even need to say, like, you need to have observed no wind and a temperature of 0 in your data set in order to interpret that value, or something close to that. Not just individually for each one, but we'll just say, because that's more difficult to check. We'll just say it needs to be in the range of each x. 0 needs to be in the range of each x to interpret the intercept. Any questions about extrapolation there? I feel like it sounds like such a fancy thing, but it's really not. It's just saying, like, oh, is it inside our data? Is that in the scope of our data? Okay. So that's how we can interpret the intercept. It's the predicted value, essentially when all the x's are 0, which you can see based on the estimated equation, right? If you set all the x's to be 0, you end up with y hat, the predicted value being the estimated intercept. Okay, so that's why we interpret it that way. Let's get a predicted value that's not extrapolation. Okay. So let's suppose, yeah, it's a 70-degree day and we have no wind. Okay, so a beautiful day at the beach. What do we predict the wave heights will be? So anytime we're getting a predicted value, I think it's always a good idea to copy the whole estimated equation. Just start with that. And then fill in the numbers. Okay. And simplify. So what should we put in for x1? Yeah, so x1 is the wind, right? Yeah, so it's 0. And then what about x2? 70. Yeah, thanks. And then using, let's see if ChatGPT. Okay. Oh my gosh. Okay. It's making it too complicated. There we go. Okay, I got it right though. 0.066. Good for you. So, oops. 0.066. So we got 0.066, and then we want to make sure we always add on what the units of measurement are. Feet. Whenever you're getting a predicted value, I would say it's a good idea to just think about briefly afterwards, like, does that seem ballpark or about right? You know, so here it's saying that if it's 70 degrees out, no wind at all, there's very little waves. That seems reasonable, right? Just as like a double, it's like a quick check on your, you know, maybe you made an arithmetic mistake. Something. Like this is always really helpful when I'm, like, I use linear regression or similar predictive models to predict like college basketball game scores. And so when I get my predictions, always as like a quick check to make sure everything was coded right and that it makes sense. I look at like some really good team versus a really bad team, and I make sure like, okay, the model should say they win by a lot. And if they don't, it's like, that's probably did something wrong in terms of how we got those predicted values. So always good to do a quick check. Yeah, so that's how we can interpret estimates from the multiple linear regression model. This is how we can get predicted values using the estimated regression equation output. Yeah, now we'll talk about some slightly more like theoretical or statistics related concepts with the estimated regression equation. Okay. So statistics is all about, like everything in statistics pretty much is assuming some relationship holds in the data between some variables. We have some unknown values that define that relationship, and then we use a data set to like estimate those values. For simple linear regression, when we did that, it involved, we look at the simple linear regression model. Okay. We assumed this was the relationship, and it involved estimating beta naught hat, beta 1 hat. And actually, it's not super evident from the regression equation, but we also end up estimating the variance of the residuals. Okay. That's involved in the estimation process. Okay. So we had 3 total parameters, 3 total things that we were estimating for simple linear regression. Okay. Which is always the same. For any simple linear regression problem, it's always 3 parameters. What about for multiple linear regression? If we have k predictors, how many parameters are we estimating them? So let's say like, let's say we had 3 predictors. How many parameters would we have then? We would have 5, right? Okay, so yeah, so 3. Right. Yeah, so k equals 3 would lead us to 5 parameters. And then in general, we have to estimate k plus 2 parameters. The reason being, we always have one intercept, and we always have one set of errors for which we estimate this term for. But then the number of slopes that we have to estimate is equal to the number of predictors. So it's like these 2 things plus the number of predictors. That's what gives us the k plus 2. I'll write that in parentheses maybe. So like the intercept, call that like the standard error of the regression model. And each of the k slopes, or the k betas. This is actually the squared. It's like the square of the standard error of the regression model. So why do I even bring that up? Well, you know, other than just like, well, it's a question we can ask about it. Well, it's always important in stats and statistics to recognize how big your sample size is and how many things you're estimating. In general, you want your sample size to be bigger than the number of parameters you're estimating. Okay. If we had like a sample size of like 12, and then we tried to have a model with 20 predictors, you would get really, like the estimates get really unreliable. And in some cases, actually, the software can't even calculate it, okay, because the sample size is not as big as the number of parameters you're estimating. Intuitively, one way to think about it is that you don't have enough information to reliably describe those relationships anymore. You need to have your sample size bigger than the number of parameters that you're estimating. Usually that's okay. Like up here, it wasn't even close because we had 69 observations and we were only estimating 4 parameters. So that's good. But yeah, there's other settings where it's easy to find yourself estimating many more things. Right. So talking about how these regression estimates are found, I don't think you'll ever get into the calculus of this unless you take Stat 415, the mathematical statistics class. But one way to think about it is that, or one like solution to get these is to use calculus and derivatives to minimize the sum of squared errors term, the SSE. Okay. That's the solution that SAS gives us, okay, for each of these betas, which involves a lot of linear algebra. But with software, with computers, that's not so bad. Okay. So yeah, if we think about in simple linear regression, maybe I'll draw it out here since we're on the video. Try to do this in Zoom here. Okay, we have like a scatter plot, and then we have X and Y. Right? Okay, let's suppose we have our data points. It's a little bit big. So we have X and Y, and then maybe we have our data points like this. Yeah, this is better. Okay. So that's like the relationship in our data. And then the goal of, okay, so first just talking about simple linear regression, right? The goal is to find a straight line that fits this data well, right? What does it mean to fit that data well? So we can draw it and we can kind of think about like, okay, yeah, like drawing it through the middle like this is pretty good. So this line is defined by the intercept, the y-intercept, and then the slope. Those two things uniquely identify it. So again, software finds this best line of fit, the straight line of best fit using calculus. And talking about intuitively how that's working, okay, is that each point has a corresponding residual, right? So if we think about the distance of every point to the line of best fit, like this gives the length of this line gives the size of that residual. And sometimes they're below, right? It's like straight up. And then some of these are really tiny. How the solution works is that we take the length of each of these lines, which represents the size of the residual, and we square those. Okay, so maybe you could think of it like each one makes a box. Yeah, listen, it's actually like, maybe I'll draw that because that's actually how it is. Right, so it's like this, actually, if this were like a square. Can we get it so it's a square that touches the line? Yeah, just like that. Okay. So this is actually how, like, graphically, one way to visualize this is that each of these, for each point, you have like a square, which is representing the square of the straight line error, the size of the residual squared. So it's like this for this point down here. This one. Okay. This square is going to be tiny because this point's really, really close. Same with this one. Okay. And what the calculus does essentially is it finds the straight line through these points that will minimize the sum of the size of all the squares. So if you like summed up the area of each of these red squares, that gives you the SSE value. And SAS, when it's finding the solutions, it finds the straight line that minimizes the size of these squares. Again, we're not going to worry about what the derivatives are or like how calculus does that, but graphically, that's the idea. And this is for simple linear regression. Yeah, this one has a tiny square too. This is another way to visualize like why outliers or influential points are potentially problematic. Because let's say like we had a point that's like way out here. Okay, and like down. Say it's way down here. How's that square gonna look? Or like, what's the square of the residual for this point gonna look like? It's gonna be huge, actually. So if we do this, because it needs to be a square too, it's not a rectangle. Here's like the penalty, or like the amount of error that this single point is contributing. So this is why outliers or influential points are problematic here like this, because when the software is finding the solution, it sees all these other points and it's like, okay, yeah, let's try to minimize the size of those squares. But then it's like this one, it's like, oh, that's a huge problem. So it needs to, it pulls the whole regression line towards that because that square is so big as it does that. Yeah, that's sort of one way to visualize the effective outliers there. But any questions about that? I'm not going to quiz on that or test on that or anything, but I think it's helpful to think about graphically how this line of best fit is found. So for multiple linear regression, it gets more complicated to visualize this because you're in like, you have more dimensions, you're in a higher dimensional space now, right? even with just two predictors, okay, you now have this situation where it's like we are salute. We're in this like three-dimensional space. And this is just two predictors. So maybe you have like x1 over here, and then this axis is x2. And then up here you have y. Okay. So maybe y is like the wave heights, right, in our case. And then here you have x1 is wind speed, and x2 is the temperature. Okay. Then for the points, okay, they're like floating in this three-dimensional space. Okay, where they have like a three-dimensional coordinate, like how tall they are, how high they are up off the ground here, and then like how far in the x1 and x2 direction they are. It's actually, it's hard to draw in three-dimensional space. You can't really do it that well on Zoom, but okay. And now how this, like, for two predictors, like what our estimates look like. So before, our estimates all fell on a straight line. Now it's like we have a plane, a flat surface floating in space. And that's where all our predicted values lie on now for two predictor multiple linear regression. And the idea for what this is doing here is that maybe I'll draw it in green. You have like a distance from that point in three-dimensional space, either up to the plane or down to the plane. Okay. And then the software, when it finds the solution, it defines this, it minimizes the square of those distances. Okay. It's like graphically how multiple linear regression is working. And as you get three predictors, it's not a plane anymore. It's, they call it like a hyperplane, I guess, but it's harder to visualize as you get in more dimensions, and it gets to be nearly impossible, right? But two dimensions, you can still kind of visualize it, that it's this perfectly flat surface with a constant slant to it for two predictor regression. Okay. All right. And so, yeah, again, like I said, we're not going to worry about the calculus for how that works, but I think it's good to have an understanding of visually what our predicted values are doing or what's going on there. Any questions about that? Okay. And like I said, if you take 415, stat 415, you'll get to, to arrive those estimates yourself, I think. So. Okay. So yeah, we talked about how many parameters we're estimating when we have a number of predictors. We also, just like we had for one-way ANOVA, there is an ANOVA table for regression as well. It's still called the ANOVA table because you're analyzing the variance in the response variable y that is explained by your model, the amount of variance in y that's not explained by your model, and then the total variance in y. Okay. And yeah, the reason being that we have this for both ANOVA and regression is, again, because ANOVA is a specific case of regression. So that's why there's still this ANOVA table. So the degrees of freedom for the model, DF model, is always going to be K, your number of predictors in the ANOVA table for multiple linear regression, n minus K minus 1 for the error degrees of freedom, and the total degrees of freedom is just n minus 1. You'll notice that this ANOVA table has the same nice properties as one-way ANOVA had, where you can sum down the column here. So K plus this gives you n minus 1. So you can always solve for like one of the cells if you're missing one of the three. And the same goes for the SS values. SS model plus SSE gives you SS total still. Okay. I give the mathematical, like, formal notations here for how you would calculate these by hand. We're not going to do that by hand, but that's, again, this is how SAS does it. I guess important things to know are this, this sum of squares identity, it's called, this equation that relates the SS values. Also that we can get an estimate of we call it the standard error of the multiple regression model. That's always equal to the square root of SSE over its degrees of freedom. Okay, the error degrees of freedom. So note that that's actually the same as the square root of MSE, because MSE is equal to SSE divided by error degrees of freedom. Okay, so the square root of the MSE gives us this. Okay. So that's the quickest way to calculate it from the ANOVA table. So I was answering that part here, essentially. And yeah, we're at time. So we'll pick up here next time and continue with this activity.